Tonight, we're going to explore something that sounds like pure science fiction, but is actually one of the most unsettling possibilities in modern physics: vacuum decay. You've probably heard about the vacuum of space before. Empty space, nothingness. Scientists talk about it constantly when describing the cosmos. But here's what most people don't realize: the vacuum isn't actually empty. It's filled with invisible fields that give particles their mass and define the very laws of physics. And according to our best theories, this vacuum might not be stable. It might be what physicists call a false vacuum, a temporary state that could spontaneously collapse into something else entirely. If that happened, a bubble of true vacuum would form and expand outward at nearly the speed of light, rewriting the laws of physics as it went. Everything we know, every atom, every star, every galaxy would simply cease to exist, and we would never see it coming. By the end of tonight, you're going to understand why some of the smartest physicists in the world think this might be the ultimate fate of our universe. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. When you step outside on a clear night and look up at the stars, you're experiencing one of humanity's oldest illusions. You see darkness between the points of light, emptiness, vast stretches of nothing separating the celestial objects that populate our universe. This intuition runs so deep that we barely question it. Space, after all, is where things happen to be, not something that exists in its own right. It's the stage, not the play. The container, not the contents. For thousands of years, this seemed perfectly reasonable. What could be simpler than nothing at all? But you're not looking at nothing. You're looking at one of the most sophisticated and dynamic structures in all of physics, disguised as emptiness. What we call the vacuum of space is not an absence but a presence, not a void but a medium, not nothing but something so fundamental to reality that without it, the very concept of matter as we know it would be meaningless. This realization represents one of the most profound shifts in our understanding of the cosmos, and tonight you're going to see why it changes everything. The story begins with a simple question that turns out to have a not-so-simple answer. What is empty space made of? Your first instinct might be to say that's a nonsensical question. Empty space isn't made of anything. That's what makes it empty. But modern physics tells a different story. When you remove every particle, every atom, every trace of matter and energy from a region of space, something remains. Not nothing. Something. A web of invisible fields that permeate every cubic centimetre of the universe, including the space between your atoms, the space inside your atoms, and the space that separates the galaxies. These fields are not science fiction. They're as real and measurable as the electromagnetic field that lets your radio work, or the gravitational field that keeps your feet on the ground. We call one of them the Higgs Field, after the physicist Peter Higgs who helped predict its existence. This field has a remarkable property. Unlike other fields, which have a value of 0 when nothing is happening, the Higgs field has a background value everywhere in space. It never turns off. It never goes to 0. It fills the vacuum with a subtle but crucial presence that shapes the fundamental nature of reality. Here's where the story becomes both beautiful and unsettling. This background value of the Higgs field is what gives particles their mass. Not some of their mass, all of their mass. Without this field, electrons would be massless. Protons would be massless. Every particle in the standard model of physics would zip around at the speed of light, unable to slow down, unable to bind together, unable to form the atoms that make up stars and planets and you. The Higgs field doesn't just fill empty space. It determines what kinds of particles can exist and how they can behave. It's not just the stage where physics happens, it's part of the script. But this raises a question that will follow us throughout tonight's journey. If the Higgs field has a background value, why that particular value? Is it the lowest possible energy state the field can have? Or could there be an even lower state, a deeper valley in what physicists call the potential energy landscape? This isn't an abstract mathematical curiosity. If our vacuum is not the lowest energy state, if it's what physicists call a false vacuum, then it's only temporarily stable. Like a ball balanced in a shallow depression on a hillside, it could, in principle, roll down to a lower level. The implications of this possibility extend far beyond academic physics. If our vacuum is false, then everything we call reality exists in a state of cosmic metastability. The laws of physics as we know them, the masses of particles, the strength of forces, the very possibility of atoms and molecules, and chemistry and life, all depend on the Higgs field maintaining its current background value. Change that value and you change everything, not just rearrange the furniture of reality. Rewrite the fundamental rules that determine what furniture can exist. This is not a story about fear, though the implications are stark enough to deserve our attention. This is a story about scale and perspective, about how the universe can be both more fragile and more robust than we ever imagined. It's about learning to think clearly about concepts that challenge our everyday intuitions about stability and permanence. The universe has existed for nearly 14 billion years in what appears to be exactly the same vacuum state we inhabit today. If our vacuum is false, it has nonetheless proven remarkably durable. What makes this more than philosophical speculation is that we can actually investigate it. Through decades of careful measurement and theoretical development, physicists have learned to probe the properties of the Higgs field with extraordinary precision. We know its mass. We know how it interacts with other particles. We can calculate how its behavior changes at different energy scales. And when we extrapolate these calculations to the highest energies, we find something remarkable and troubling. Under certain conditions, with certain values for the fundamental constants, the Higgs field might indeed prefer a different configuration than the one we observe. The vacuum beneath your feet, the vacuum between the stars, the vacuum that fills the space between galaxies, might be whispering a secret. It might be temporary, not unstable in any human sense of time, but not eternal either. Balance between existence and transformation, hosting a universe rich enough to contemplate its own foundations, yet potentially subject to the most complete change imaginable. Tonight, you're going to learn how we discovered this possibility, what it might mean, and why the question of vacuum stability has become one of the deepest and most fascinating problems in modern physics. To understand how a field can give weight to the world, you need to first understand what physicists mean when they talk about fields. This is one of those concepts that sounds abstract until you realize you've been experiencing fields your entire life. Right now, as you listen to these words, you're immersed in the Earth's magnetic field. It's invisible, intangible, yet completely real. You can detect it with a compass. You can map its strength and direction. It extends far beyond the planet's surface, shaping the aurora in our atmosphere and deflecting charged particles from the sun. The magnetic field is just one example of something that fills space continuously. Unlike particles, which exist at specific locations, fields have a value at every point in space and time. Think of a field as information spread throughout the universe, information that tells particles how to behave when they encounter it. The electromagnetic field carries information about electric and magnetic forces. The gravitational field carries information about how masses should attract each other. Each field creates a kind of landscape of influence that permeates reality. But among all the fields that physics has discovered, the Higgs field stands apart. Most fields, when left undisturbed, settle down to a value of 0. The electromagnetic field, for instance, has 0 strength in empty space when no charges or currents are present. Remove all sources and the field disappears. The Higgs field behaves differently. Even when you remove every particle, every disturbance, every source of energy from a region of space, the Higgs field maintains a constant non-zero value throughout that region. It never turns off. It never goes away. It forms a kind of cosmic background that fills every corner of the universe. Imagine walking through fresh snow. Each step requires effort because you're constantly pushing through the medium that surrounds you. The deeper the snow, the more resistance you feel, the more energy each step demands. Now imagine that this snow is invisible and fills all of space, and instead of slowing down your footsteps, it determines how much you weigh. This captures something essential about how the Higgs field works, though the analogy needs refinement. The Higgs field doesn't create friction in the usual sense. It doesn't slow particles down through resistance. Instead, it interacts with them in a way that manifests as mass. Think of it this way. When a particle moves through the Higgs field, the strength of its interaction with that field determines how we measure its mass. Particles that interact strongly with the Higgs field, like the top quark, have large masses. Particles that interact weakly, like electrons, have small masses. Particles that don't interact with the Higgs field at all, like photons, remain massless and travel at the speed of light. The field doesn't add mass to particles like cargo added to a truck. It creates the very property we call mass through the mechanism of interaction. You might wonder how we know this isn't just an elaborate theoretical construction. How can we be certain that this invisible field really exists? The answer came on July 4, 2012, when physicists at the Large Hadron Collider announced the discovery of the Higgs boson. This discovery represents one of the most sophisticated detective stories in the history of science. You can't observe the Higgs field directly, but you can disturb it. When you pump enough energy into a small region of space, you can create ripples in the field, and those ripples manifest as particles we can detect and measure. The Higgs boson is to the Higgs field what ripples are to the surface of a pond. Strike the water, and you create waves that spread outward, carrying information about the disturbance. Strike the Higgs field with sufficient energy, and you create a particle that quickly decays into other particles, leaving traces in our detectors. By studying these traces, physicists can reconstruct the properties of the original particle and, by extension, the field that produced it. The measurements tell us that the Higgs boson has a mass of approximately 125 billion electron volts, expressed in the units physicists prefer. This number anchors our understanding of the field in experimental reality. But here's where the story becomes more intriguing. The Higgs field doesn't just give mass to other particles, it also interacts with itself. This self-interaction is encoded in what physicists call the Higgs potential, a mathematical description of how the field's energy changes with its value. Think of this potential as a landscape of valleys and hills that determines where the field prefers to settle. The deeper the valley, the more stable the configuration. The field naturally seeks the lowest energy state, just as a marble rolling on a curved surface seeks the bottom. Our current understanding suggests that the Higgs field has settled into a valley in this energy landscape, giving it its observed background value throughout space. This valley is deep enough to be stable under normal circumstances, but the question remains whether it represents the absolute bottom of the landscape or merely a local depression with deeper valleys elsewhere. If deeper valleys exist, then the field's current state, stable as it appears, might be only temporarily so. The mathematics of the Higgs potential depends critically on the exact masses of particles, especially the heaviest ones like the top quark. Small changes in these measured values can shift our understanding of the potential landscape dramatically. With our current measurements, the potential appears to have a complex structure at high energies, one that might include regions where the field would prefer a different value than the one we observe. This possibility connects the seemingly abstract world of quantum field theory to questions about the ultimate fate of everything we know. If the Higgs field can determine something as fundamental as the mass of every particle in the universe, what else might its particular configuration control? The strength of nuclear forces, the stability of atoms, the rate of chemical reactions, the very possibility of complex structures like stars and planets and life itself. All of these depend on particles having the specific masses that the Higgs field currently provides. Change the field's value, and you don't just adjust the properties of matter, you rewrite the rules that govern what kinds of matter can exist at all. There are thoughts in physics that seem to end the story before it begins. Ideas so complete in their implications that they appear to close off all possibilities for discussion, all room for hope, all reason to continue thinking. Vacuum decay is one of these thoughts. When you first encounter the concept, it feels less like a scientific theory and more like a cosmic period at the end of every sentence about the future. But this initial reaction, while understandable, misses something crucial about how science allows us to think clearly about even the most unsettling possibilities. The thought begins with a deceptively simple premise. What if the vacuum state that fills our universe, the background configuration of the Higgs field that gives particles their masses and determines the laws of physics, is not the lowest possible energy state? What if it's what physicists call a false vacuum, a configuration that appears stable but is actually metastable, like a ball resting in a shallow depression on the side of a hill? The ball might sit there for an enormously long time, appearing perfectly stable, but it's not at the bottom of the hill. Deeper valleys exist below. In quantum mechanics, nothing stays perfectly still forever. Even the most stable-seeming systems experience fluctuations, tiny random variations that probe all possible configurations. Most of these fluctuations lead nowhere, like gentle nudges that rock the ball slightly in its depression before it settles back. But quantum mechanics allows for rare events, improbable fluctuations that can overcome barriers that would be insurmountable in classical physics. A quantum fluctuation, vanishingly unlikely but not impossible, could push the Higgs field from its current value toward a lower energy state. If this happened, if such a fluctuation occurred in even a tiny region of space, something extraordinary would begin. The field in that region would start to roll toward the true vacuum state, the configuration of lowest possible energy. But fields don't transition everywhere at once. Instead, the transition would create a boundary, a bubble wall separating the region of true vacuum from the surrounding false vacuum. Inside the bubble, physics would operate according to different rules. Outside, everything would remain as it always has been. But bubbles of true vacuum, once formed above a critical size, do not remain small. The mathematics of quantum field theory tells us something both elegant and terrifying about their behavior. The bubble wall would begin to expand outward in all directions, accelerating as it grows, asymptotically approaching the speed of light. Inside the expanding bubble, the Higgs field would have its new value, particles would have different masses, forces would have different strengths, and the laws of physics as we know them would no longer apply. This is where the story acquires its most chilling feature. Light travels at the ultimate speed limit of cause and effect. Information cannot travel faster than light. No signal, no influence, no warning of any kind can outpace a light beam. But if a bubble of true vacuum expands at nearly the speed of light, its leading edge would arrive at Earth at essentially the same moment as any light signal that might theoretically warn us of its approach. There would be no advance notice, no time to prepare, no opportunity to observe the approaching transformation from a safe distance. The boundary itself would be a region where the fundamental constants of nature transition from their familiar values to whatever values they possess in the true vacuum. As this boundary swept past Earth, past the solar system, past our galaxy, it would rewrite the rules of physics in its wake. Atoms might become unstable, nuclear forces might weaken or strengthen beyond recognition. The masses of particles might change so dramatically that the structures we call matter could no longer maintain their integrity. What would happen to a human being, to a planet, to a star, caught in such a transition? The honest answer is that we don't know. We can outline categories of change, but not their specific consequences. We can say that the physics inside the bubble would be different, perhaps radically different from the physics we observe. But whether different means merely exotic or completely incompatible with complex structures like life remains an open question. You might expect this possibility to provoke existential dread, and certainly many people experience exactly that reaction when they first encounter vacuum decay. But there's another way to think about it, one that doesn't minimize the starkness of the concept, but places it in a broader context of scientific understanding. Physics is not in the business of providing comfort, but it is in the business of providing perspective. The mere fact that we can discuss vacuum decay, that we can calculate probabilities and analyze scenarios, represents a remarkable achievement of human understanding. We have developed theories sophisticated enough to contemplate the conditions of their own applicability. We have learned to think clearly about possibilities that transcend ordinary experience. This is not a failure of science, but one of its greatest successes. Moreover, the ability to formulate the concept of vacuum decay does not imply that such an event is imminent or even likely within any timeframe relevant to human concerns. The calculations that predict metastability also predict timescales so vast that they dwarf the current age of the universe by factors that strain comprehension. Even if our vacuum is false, it has already demonstrated a durability measured in billions of years. What vacuum decay teaches us is not that we should fear the future, but that we should appreciate the extraordinary stability of the present. The vacuum that surrounds us, fills us, and defines the possibilities for our existence has maintained its current configuration throughout the entire history of stars and galaxies and life on Earth. Whether this represents absolute stability or merely impressive metastability, it testifies to the remarkable hospitality of the universe we inhabit. Tonight, we're going to earn our way slowly through each step of this reasoning. We'll build the mathematical intuition, explore the physical mechanisms, and examine the observational evidence that leads physicists to take vacuum decay seriously. By the end of our journey, you'll find that this concept, initially so stark and final, becomes something you can contemplate with clarity rather than fear, understanding rather than dread. To understand what physicists mean when they say our vacuum might be unstable, you need to learn to think like a marble. Not in terms of consciousness or decision-making, but in terms of energy and the relentless tendency of physical systems to seek their lowest possible energy state. This is one of the most fundamental principles in all of physics, yet it's often hidden beneath the complexity of equations and the abstraction of mathematical formalism. Tonight, we're going to make it visible through the simple but powerful concept of an energy landscape. Imagine standing on a hillside dotted with valleys of different depths. Some valleys are shallow depressions that barely interrupt the slope. Others are deep basins carved into the bedrock. If you place a marble anywhere on this landscape and give it a gentle push, it will roll downhill, seeking the lowest point it can reach. But here's the crucial insight. The lowest point the marble can reach depends not just on the landscape, but on where the marble starts and how much energy you give it to begin its journey. A marble that starts in a shallow depression might settle there and remain motionless for hours, days, or years. To a casual observer, it appears completely stable. But if you could see the entire landscape, you might notice that this depression sits on the side of a much larger hill, and far below, barely visible in the distance, lies a valley so deep that if the marble could somehow reach it, it would never leave. The marble in the shallow depression is not truly at rest. It's trapped by circumstances, not by physics. This is the essence of what physicists call metastability. A system is metastable when it occupies a local minimum in its energy landscape, a configuration that is stable against small disturbances, but not necessarily the lowest energy state available to the system. The marble in the shallow cup appears stable because small nudges will only cause it to rock gently before settling back into place. But a sufficiently large disturbance, one that provides enough energy to lift the marble over the rim of its depression, could set it rolling toward a much lower point on the landscape. The distinction between stable and metastable states is not academic. It determines the ultimate fate of physical systems across vast ranges of scale and complexity. A metastable atomic nucleus might remain unchanged for billions of years before suddenly decaying in a radioactive event. A metastable chemical compound might appear perfectly inert under normal conditions, but transform rapidly when exposed to the right catalyst or temperature. The concept of metastability allows physicists to understand why some configurations persist for enormous periods of time, even when they are not the most energetically favorable arrangements possible. But here's what makes metastability so fascinating and, in some contexts, so unsettling. The lifetime of a metastable state can vary dramatically depending on the height and width of the energy barrier that separates it from lower energy configurations. A shallow barrier might be overcome relatively easily, leading to rapid transitions. A high, wide barrier might prevent transitions for timescales that exceed the age of the universe. Metastability is not synonymous with imminent collapse. It can represent extraordinary longevity combined with ultimate impermanence. The mathematics that describe energy landscapes apply to quantum fields just as they apply to marbles on hillsides. Every field in physics has what's called a potential energy function, a mathematical description of how the field's energy changes as its value changes. You can visualize this potential as a landscape where the horizontal axis represents the field's value and the vertical axis represents energy. Valleys in this landscape correspond to stable or metastable configurations of the field. Peaks and ridges represent unstable configurations that the field will quickly abandon. The Higgs field, like every other field in physics, has its own potential energy landscape. The shape of this landscape determines where the field prefers to settle and how stable that configuration will be. Our current measurements suggest that the Higgs field sits in a valley that corresponds to its observed background value throughout space. This valley is deep enough to explain why the field has maintained the same value for the entire observable history of the universe. But the question that drives much of modern particle physics is whether this valley represents the absolute bottom of the landscape or merely a local depression with deeper valleys lying elsewhere. The shape of the Higgs potential depends on parameters that can, in principle, be measured experimentally. The mass of the Higgs boson itself provides one crucial piece of information. The masses of other particles, particularly the heaviest ones like the top quark, influence the potential at high energies through quantum mechanical effects. Small changes in these measured values can dramatically alter the predicted shape of the potential landscape, shifting our understanding from absolute stability to metastability, or vice versa. This is where the story connects to the cutting edge of experimental physics. Teams of scientists working at the world's most sophisticated particle accelerators are engaged in a meticulous effort to measure these parameters with ever-increasing precision. Each decimal place in the mass of the top quark, each refinement in the measurement of the Higgs boson's properties, potentially shifts our understanding of the landscape in which our universe exists. Current measurements place us tantalizingly close to a boundary in parameter space, a region where small changes in the fundamental constants could tip the balance between stability and metastability. Some calculations suggest that with our best current values, the Higgs potential might indeed have a second, deeper valley at very high field values. If this is correct, then our apparently stable vacuum would be revealed as metastable, a long-lived but ultimately temporary configuration. The implications of this possibility extend far beyond abstract physics. If the Higgs field is currently sitting in a local minimum rather than a global one, then everything that depends on the field's current value, everything from the masses of particles to the strength of forces to the very possibility of complex chemistry, exists in a state of cosmic metastability. Not precarious in any human sense of time, but not eternal either. The universe would be like a marble, resting peacefully in its depression, unaware of the deeper valleys that lie beyond the barriers that currently protect it. In the everyday world of classical physics, barriers mean exactly what they seem to mean. A ball rolling toward a hill will either have enough energy to go over the top, or it won't. If it doesn't, it stops, rolls back, and that's the end of the story. A marble in a cup needs sufficient energy to climb over the rim before it can escape to lower ground. These rules feel intuitive because they match our daily experience with objects large enough to see and touch. Energy is energy, barriers are barriers, and insufficient means insufficient. But the quantum world operates by a different and far more subtle set of rules. At the scale of atoms and subatomic particles, the sharp boundaries of classical physics dissolve into something more nuanced. Quantum mechanics tells us that particles don't have definite positions and energies in the way that classical objects do. Instead, they exist as probability distributions, clouds of possibility that describe where they might be found and what energy they might have when measured. This fundamental uncertainty creates opportunities that simply don't exist in the classical world. Consider a particle approaching a barrier that it classically cannot overcome. In the classical picture, the particle bounces back every time, forever trapped on one side of the obstacle. But in quantum mechanics, the particle's wave-like nature allows something remarkable to occur. Even when the particle lacks sufficient energy to go over the barrier, there exists a small but finite probability that it can pass through the barrier as if it weren't there. This phenomenon is called quantum tunneling, and it's not a violation of energy conservation or a breakdown of physical law. It's a fundamental feature of how reality works at its deepest level. Tunneling happens because the quantum description of a particle includes the possibility that it can be found on the far side of a barrier even when it doesn't have enough energy to climb over it classically. The probability of tunneling depends on several factors: the height of the barrier, its width, and the mass of the particle. Higher barriers suppress tunneling. Wider barriers suppress it even more. Heavier particles tunnel less readily than lighter ones. But no barrier, no matter how high or wide, can reduce the tunneling probability to exactly zero. This might sound like an exotic curiosity relevant only to particle physics experiments, but tunneling shapes the world around you in ways both subtle and profound. The fusion reactions that power the sun depend on quantum tunneling. The protons in the solar core lack the energy to overcome their electrical repulsion classically, but tunneling allows them to merge and release the energy that has warmed Earth for billions of years. The scanning tunneling microscope uses quantum tunneling to image individual atoms. Even the alpha decay of radioactive nuclei occurs through tunneling, as particles escape from the nuclear potential well, despite lacking sufficient classical energy. But perhaps the most profound application of tunneling involves not particles escaping from atoms or merging in stellar cores, but entire regions of space transitioning between different vacuum states. Just as a particle can tunnel through a barrier it classically cannot overcome, a quantum field can tunnel from one energy configuration to another, even when separated by energy barriers that would classically forbid such transitions. This is the physical mechanism that could, in principle, drive vacuum decay. In the context of the Higgs field, tunneling takes on a meaning that extends far beyond individual particles. If the field currently sits in a local minimum of its potential energy, separated from a deeper minimum by an energy barrier, quantum mechanics allows for the possibility that the field could tunnel through that barrier to the lower energy state. But fields don't tunnel particle by particle or location by location. Instead, the tunneling process involves the spontaneous formation of a region, a bubble, where the field has made the transition to the new configuration. The probability of such an event is extraordinarily small for any given point in space and time. Physicists describe this using the concept of a decay rate per unit volume, a number that tells you the probability per unit time that a transition will occur in a given volume of space. Even for a metastable vacuum, this rate is typically so small that it defies intuitive comprehension. You might wait longer than the current age of the universe and never see a single tunneling event in a volume the size of our solar system. But here's where the vast scale of the universe transforms extremely improbable events into statistical inevitabilities. The observable universe contains a volume of space measured in cubic light-years that exceeds 10 to the 78 power. Even a decay rate so small that it seems negligible becomes significant when multiplied by this enormous volume. A probability that is vanishingly small in your backyard becomes measurable when considered across all the space in all the galaxies we can observe. Moreover, the universe has existed for nearly 14 billion years, providing not just vast volumes of space, but vast stretches of time for rare events to occur. When you multiply a tiny probability per unit volume, per unit time, by the total space-time volume of the observable universe, events that seem impossibly unlikely in human terms become statistically expected over cosmic scales. This is the mathematical foundation underlying all discussions of vacuum decay. The transition from a false vacuum to a true vacuum doesn't require special conditions or external triggers. It simply requires patience and the enormous space-time volume that the universe provides. Quantum mechanics guarantees that if our vacuum is metastable, tunneling events will eventually occur. The only question is when and where. When such a tunneling event happens, it doesn't transform the entire universe instantaneously. Instead, it creates a seed, a small bubble of true vacuum embedded in the surrounding false vacuum. The physics of what happens next depends on the detailed energy balance between the interior and exterior of the bubble, the surface tension of the bubble wall, and the curvature of space-time itself. In many scenarios, once formed above a critical size, these bubbles begin to grow, expanding outward and consuming more false vacuum as they go. The combination of quantum tunneling and cosmic scale transforms vacuum decay from a theoretical curiosity into a process that cosmologists take seriously. It's not magic, it's not mysticism, and it's not science fiction. It's the inevitable consequence of quantum mechanics applied to field theory over the vast expanses of space and time that characterize our universe. When quantum tunneling creates a bubble of true vacuum within a false vacuum, the story that follows is governed by one of the most elegant and terrifying pieces of physics ever developed. The mathematician Sidney Coleman, working in the 1970s, provided the theoretical framework that describes how such bubbles behave once they come into existence. His analysis reveals a process that is both mathematically beautiful and cosmically unsettling, a phenomenon that operates according to precise physical principles, yet leads to consequences that challenge our deepest intuitions about stability and permanence. To understand bubble dynamics, you need to think about energy in two different forms. The first is the energy stored in the bubble wall itself. This wall represents the boundary between two different vacuum states, a region where the Higgs field transitions from its current value outside the bubble to its new value inside. Creating this boundary requires energy, just as stretching a rubber membrane requires energy. The thicker the wall, the more energy it contains. The larger the bubble, the greater the total energy stored in its surface. The second form of energy is the difference between the vacuum energy inside and outside the bubble. If the true vacuum inside the bubble has lower energy than the false vacuum outside, then every unit of volume that transitions from false to true vacuum releases energy. The larger the bubble, the more volume it contains, and the more energy is released by the vacuum transition. These two effects, surface energy that costs energy and volume energy that releases energy, compete with each other in a way that determines whether a bubble will grow or collapse. Small bubbles are dominated by surface energy. Like soap bubbles in air, they experience an inward pressure that tends to make them collapse. The energy required to maintain the bubble wall exceeds the energy gained by converting false vacuum to true vacuum within the small interior volume. But as bubbles grow larger, the volume effect begins to dominate. Beyond a critical radius, the energy released by vacuum conversion more than compensates for the energy cost of maintaining the bubble wall. At this point, the bubble becomes energetically favored to expand rather than contract. This critical radius represents a watershed moment in the physics of vacuum decay. Bubbles smaller than this critical size will shrink and disappear, flickering into existence through quantum tunneling, only to collapse back into the surrounding false vacuum. But bubbles that form above the critical size face a very different destiny. For these bubbles, expansion lowers the total energy of the system. Physics, with its relentless tendency to seek lower energy states, drives such bubbles to grow without limit. Coleman's analysis revealed that once a bubble exceeds the critical size, it doesn't simply expand at some modest, controllable rate. Instead, the bubble wall accelerates outward, driven by the energy difference between the interior and exterior vacuum states. The wall rapidly approaches a terminal velocity that is asymptotically close to the speed of light. This is not the result of some exotic propulsion system or violation of relativity. It's the inevitable consequence of energy conservation applied to the bubble expansion process. The approaching light speed of the bubble wall creates the scenario that makes vacuum decay uniquely ominous among cosmic catastrophes. Most disasters, even cosmic ones, provide some form of advance warning. You can see a comet approaching from the outer solar system. You can detect the gravitational waves from merging black holes billions of years before they affect Earth. You can observe the signs of stellar instability long before a supernova occurs. But a bubble of true vacuum expanding at nearly the speed of light provides no such courtesy. Light itself travels at the ultimate speed limit for cause and effect in the universe. No information, no influence, no signal of any kind can travel faster than light. This means that if a bubble wall approaches at 99.9% of light speed, any light signal that might theoretically warn us of its approach would arrive only moments before the wall itself. There would be no time to observe the approaching transformation, no opportunity to study it from a distance, no possibility of preparation or response. The physics becomes even more subtle when you account for the curvature of space-time itself. Einstein's general relativity tells us that energy and matter curve the geometry of space and time, and vacuum energy is no exception. Coleman, working with Frank DeLucia, extended the bubble analysis to include gravitational effects. In realistic cosmological scenarios, the difference in vacuum energy between the interior and exterior of the bubble creates gravitational fields that influence the expansion dynamics. These gravitational effects can actually accelerate the bubble expansion even further. The lower vacuum energy inside the bubble creates a gravitational environment that is subtly different from the higher energy false vacuum outside. This difference in spacetime curvature contributes additional driving force for the expansion process. In some scenarios, the bubble wall can approach the speed of light even more closely than it would in the absence of gravity, but the most profound aspect of Coleman's analysis is not the specific details of acceleration and expansion rates. It's the recognition that bubble nucleation and growth represent a fundamental phase transition in the structure of space-time itself. The bubble wall is not simply a moving boundary. It's a region where the basic parameters that define physical reality undergo radical transformation. Inside the bubble, particles have different masses, forces have different strengths, and the very rules that govern the behavior of matter and energy take on new forms. What would it mean for such a boundary to sweep past Earth, past our solar system, past our galaxy? The honest answer is that we can outline categories of change, but cannot predict specific consequences. We know that the transition would rewrite the fundamental constants of nature, but we cannot say precisely what values those constants would assume in the true vacuum. We know that the structure of atoms and nuclei depends critically on the current masses of particles, but we cannot predict whether any form of complex matter could exist under the new physics. This uncertainty does not represent a failure of theoretical physics. It reflects the fact that we are contemplating a transition so fundamental that it transcends our current theoretical framework. We are asking what happens when the basic rules that define our physical reality are themselves replaced by different rules. The question pushes against the very boundaries of what science can predict, not because the physics is unclear, but because the physics is so thoroughly transformed. Coleman's bubble dynamics give vacuum decay its particular character among cosmic scenarios. Not a gradual change that we might adapt to or flee from, but an instantaneous rewriting of physical law that arrives without warning at the speed of light itself. It is, as a simple statement of fact, terrifying. But it is also, as a piece of physics, precise and calculable and beautiful in its mathematical inevitability. One of the most unsettling discoveries in modern physics is that the fundamental constants of nature are not actually constant. This revelation emerges not from sloppy measurements or theoretical confusion, but from the deep mathematical structure of quantum field theory itself. The numbers that define the strength of forces, the masses of particles, and the shape of potential energy landscapes change subtly but systematically as you probe physics at different energy scales. This phenomenon, known as the running of coupling constants, transforms questions about vacuum stability from simple yes or no determinations into complex analyses that depend critically on the energy scale at which you ask the question. To understand why constants run, you need to appreciate one of quantum mechanics' most counterintuitive features. Empty space, as we've already explored, is not truly empty. It's filled with quantum fluctuations, virtual particles that pop into existence and annihilate each other on timescales so brief that they cannot be observed directly. These fluctuations are not merely theoretical constructs. They have measurable effects on the behavior of real particles and forces. When you measure the strength of a force or the mass of a particle, you're not measuring some pristine, isolated property. You're measuring that property as modified by its interactions with the quantum fluctuations of the vacuum. The crucial insight is that the nature of these quantum fluctuations depends on the energy scale of your measurement. At low energies, you probe long-distance physics where only relatively light particles contribute significantly to the fluctuations. At high energies, you access short-distance physics where heavy particles, normally too massive to appear in low-energy processes, begin to influence the quantum corrections. As you change the energy scale of your probe, you effectively change which virtual particles contribute most strongly to the vacuum fluctuations, and this changes the apparent values of the fundamental constants. The mathematical framework that describes this energy dependence is called the renormalization group. Despite its intimidating name, the basic idea is straightforward. The renormalization group provides equations that tell you how coupling constants change as you move from one energy scale to another. These equations are not approximations or guesses. They are exact consequences of quantum field theory, derived from the fundamental requirement that physics must be consistent across different scales of observation. For the Higgs field, the most important running coupling is the one that describes the field's interaction with itself. This self-interaction, encoded in what physicists call the quartic term of the Higgs potential, determines the shape of the energy landscape in which the field sits. When this coupling is positive, it creates an upward curving potential that stabilizes the field at its current value. When it becomes negative, it creates a downward sloping potential that destabilizes the field and can lead to vacuum decay. At the energy scales we can currently probe directly, roughly a few hundred billion electron volts, the Higgs self-coupling appears to be positive, consistent with a stable vacuum. But the renormalization group equations tell us how this coupling changes as we extrapolate to much higher energies, scales far beyond the reach of any conceivable particle accelerator. This extrapolation reveals something remarkable and troubling. Under certain conditions determined by the exact masses of particles in the standard model, the Higgs self-coupling can change its sign at very high energies, becoming negative and potentially destabilizing the vacuum. The particle that plays the most crucial role in this story is the top quark, the heaviest known fundamental particle. The top quark's mass, currently measured at about 173 billion electron volts, influences the running of the Higgs coupling through quantum loop corrections. These corrections arise because virtual top quarks contribute to the quantum fluctuations that surround the Higgs field. The heavier the top quark, the stronger its influence on these fluctuations, and the more dramatically it affects the evolution of the Higgs coupling with energy. Here's where the story becomes both precise and precarious. With our current best measurements of particle masses, the renormalization group equations predict that the Higgs self-coupling will indeed turn negative at energies around 10 to the 10th or 10 to the 11th billion electron volts. This is an extraordinarily high energy scale, far beyond anything we can produce artificially, but it's still finite and calculable. At this scale, which physicists call the instability scale, the Higgs potential begins to tilt downward, creating the possibility of a deeper vacuum state at very high field values. But this prediction comes with enormous uncertainties, and these uncertainties highlight one of the most challenging aspects of theoretical physics. The extrapolation from current experimental energies to the instability scale spans more than 6 orders of magnitude. We're using equations measured at energies of hundreds of billions of electron volts to make predictions about physics at energies of 100 trillion electron volts. This is like using observations of ripples on a pond to predict the behavior of tsunami waves in the deep ocean. Small changes in the measured masses of particles, particularly the top quark and the Higgs boson itself, can shift the predicted instability scale dramatically or eliminate it altogether. If the top quark were just a few billion electron volts lighter than current measurements suggest, the Higgs coupling might remain positive at all energy scales, ensuring absolute vacuum stability. If it's a few billion electron volts heavier, the instability might appear at even lower energies than current calculations predict. This sensitivity to precise numerical values reflects a deeper feature of the standard model of particle physics. We appear to live very close to a boundary in parameter, space, a critical region where small changes in fundamental constants determine whether our vacuum is stable or metastable. This proximity to the boundary is itself puzzling. Why should the universe be so finely tuned to exist right at the edge between stability and metastability? Is this a coincidence, a selection effect, or a clue to physics beyond our current understanding? The running of coupling constants transforms vacuum stability from a simple question about the shape of a potential into a complex dynamical problem that depends on the entire history of how forces and masses change with energy. The answer depends not just on what the Higgs potential looks like at low energies, where we can measure it, but on how it evolves as we extrapolate to energy scales that existed only in the first moments after the Big Bang. This evolution is not chaotic or unpredictable. It's governed by precise mathematical equations that we can solve with high confidence. But the solutions depend sensitively on input parameters that we can measure only with finite precision. And this combination of mathematical certainty with experimental uncertainty creates one of the most intriguing puzzles in modern physics. At this moment in the history of science, we find ourselves in a remarkable position. We possess measurements of extraordinary precision for the fundamental parameters that determine the fate of our vacuum, yet these measurements place us tantalizingly close to boundaries in theoretical space, where small shifts in numerical values lead to dramatically different conclusions about the ultimate stability of everything we know. This is the frontier where experimental precision meets cosmic consequence, where the most sophisticated instruments humanity has ever built probe questions that stretch from the smallest scales of particle physics to the largest scales of cosmological time. The foundation of our understanding rests on two crucial measurements that anchor all discussions of vacuum stability. The first is the mass of the Higgs boson itself, determined through painstaking analysis of collision data from the Large Hadron Collider. After decades of searching and years of careful measurement, we know this mass to be approximately 125 billion electron volts, with an uncertainty that has been reduced to less than 1% through the combined efforts of multiple experimental teams. This number is not a theoretical prediction or an estimate based on indirect evidence. It is a direct measurement of one of nature's fundamental constants, extracted from the debris of billions of high-energy collisions. The second anchor is the mass of the top quark, the heaviest known fundamental particle and the most significant influence on the evolution of the Higgs potential at high energies. Current measurements place this mass at about 173 billion electron volts, again with uncertainties that have been systematically reduced through improved experimental techniques and more sophisticated data analysis. These measurements represent triumphs of experimental physics, achievements that required the coordination of thousands of scientists working with instruments of almost unimaginable complexity and precision. But here is where the story becomes both fascinating and unsettling. These exquisitely precise measurements place the fundamental parameters of nature in a region of theoretical space where the boundary between vacuum stability and metastability lies within the current experimental uncertainties. Small shifts in the measured values, changes smaller than the width of a human hair compared to the scales we're measuring, can tip the balance between a universe that is absolutely stable and one that exists in a state of long-lived but ultimately temporary equilibrium. Consider what this means in practical terms. If the top quark mass were measured to be just 2 or 3 billion electron volts, lighter than current best estimates, the extrapolated evolution of the Higgs potential might remain stable at all energy scales, ensuring that our vacuum represents the absolute minimum of the energy landscape. If instead the mass proves to be slightly heavier than current measurements suggest, the potential might become unstable at even lower energy scales than present calculations predict. The difference between eternal stability and eventual decay hinges on measurements at the very edge of our current experimental precision. This sensitivity reveals something profound about our location in the space of possible universes. We appear to inhabit a cosmos whose fundamental parameters lie precisely at the boundary between different regimes of behavior. This could be a remarkable coincidence, or it could be a clue to deeper physics that we don't yet understand. Some physicists speculate that we observe these particular values precisely because they are the only ones consistent with the existence of observers capable of making measurements. Others suggest that additional physics beyond the standard model might stabilize the vacuum in ways that our current theories don't account for. Even when theoretical calculations suggest that our vacuum might be metastable, the predicted timescales for decay provide a form of comfort that spans almost beyond human comprehension. The quantum tunneling rates that govern vacuum transitions are so extraordinarily suppressed that even conservative estimates yield vacuum lifetimes that exceed the current age of the universe by factors measured in tens or hundreds of orders of magnitude. These are not numbers that human intuition can grasp directly. They represent timescales so vast that galaxies will form and die, stars will exhaust their fuel and fade to darkness, and protons themselves might decay, all while our metastable vacuum continues to persist in its current configuration. The continuing experimental program in particle physics is driven partly by the recognition that small improvements in measurement precision can dramatically clarify our understanding of these fundamental questions. Teams working on the Large Hadron Collider and planning future facilities are engaged in a systematic effort to reduce uncertainties in particle masses and coupling constants. Each incremental improvement in precision, each additional decimal place in our knowledge of fundamental parameters, potentially shifts our understanding of vacuum stability from the realm of speculation into the domain of reliable prediction. The most recent measurements from experimental collaborations at CERN have achieved a precision that would have seemed impossible just a decade ago. The mass of the Higgs boson is now known with an accuracy that allows meaningful extrapolations to energy scales trillions of times higher than anything we can produce directly. The top quark mass has been measured through multiple independent techniques, each providing cross-checks on the others and steadily reducing the systematic uncertainties that once dominated the error budget. Yet even these remarkable achievements leave us in a state of informed uncertainty about the ultimate fate of our vacuum. We can calculate with confidence how the Higgs potential evolves with energy, but the calculations depend on input parameters that we know only within finite precision. We can determine whether specific sets of measured values lead to stability or metastability, but we cannot yet measure those parameters precisely enough to eliminate all uncertainty about which regime describes our actual universe. This situation reflects both the power and the limitations of modern theoretical physics. Our mathematical framework is sophisticated enough to connect laboratory measurements of particle masses to questions about the stability of the vacuum across cosmic time. We can trace the logical chain from experimental data through quantum field theory to cosmological consequences with mathematical rigor. But we cannot escape the fundamental requirement that theoretical predictions depend on experimental inputs, and those inputs carry uncertainties that propagate through our calculations. What emerges from this analysis is a picture of a universe that feels finely poised between different possible fates, not precarious in any immediate sense, but balanced on a knife's edge in the space of fundamental parameters, close enough to critical boundaries that small changes in our measurements can reshape our understanding of cosmic destiny. We exist, it seems, in a universe whose ultimate stability remains one of the most profound open questions in all of science. A question whose answer lies hidden in the precise values of numbers that we are only now learning to measure with sufficient accuracy to matter. When physicists attempt to calculate how long a metastable vacuum might persist before undergoing decay, they encounter numbers so large that they strain not only human comprehension, but even our mathematical notation systems. These calculations represent one of the most profound exercises in theoretical physics, an attempt to estimate the lifetime of reality itself using the tools of quantum mechanics and statistical analysis. The process reveals both the extraordinary power of modern theoretical methods and their ultimate limitations when pushed to the very boundaries of what can be known about the universe. The starting point for such calculations lies in recognizing that vacuum decay, if it occurs at all, operates as a stochastic process. This means it follows the same statistical principles that govern radioactive decay, but applied to the fabric of space-time itself, rather than to individual atomic nuclei. Just as a radioactive atom has no memory of how long it has existed, and no tendency to decay more readily as time passes, a metastable vacuum maintains the same probability of transition regardless of how long it has persisted in its current state. The vacuum doesn't age, doesn't accumulate damage, and doesn't become more vulnerable to decay simply because it has existed for billions of years. This timeless character of quantum decay processes leads to what physicists call exponential statistics. If you know the decay rate for a radioactive sample, you can predict that half of it will decay within one half-life, 3/4 within two half-lives, and so on. The mathematics is precise and well tested, applicable to systems ranging from individual atomic nuclei to entire populations of unstable particles. For vacuum decay, the same mathematical framework applies, but instead of calculating the probability that a particular atom will decay, you calculate the probability that a particular region of space will spontaneously nucleate a bubble of true vacuum. The decay rate for vacuum transitions depends on a quantity physicists call the tunneling action, a number that encapsulates all the relevant physical parameters: the height and width of the energy barrier, separating different vacuum states, the masses of particles that influence the tunneling process, and the detailed shape of the potential energy landscape. Calculating this action requires solving complex equations that describe how quantum fields behave in curved space-time, taking into account the gravitational effects that arise when large amounts of energy are concentrated in small regions. What makes vacuum decay calculations so challenging is that the tunneling action typically turns out to be an enormous number, sometimes reaching values of hundreds or thousands. This might not sound particularly impressive until you understand how tunneling probabilities depend on the action. The decay rate is proportional to the exponential of the negative action, meaning that if the action is 100, the decay rate is proportional to 10 raised to the negative 100 power. If the action is 1000, the decay rate becomes proportional to 10 raised to the negative 1000 power, a number so small that it defies any attempt at intuitive understanding. To appreciate what these numbers mean in practical terms, consider that the age of the universe is approximately 10 to the 10th power years, or about 10 to the 17th power seconds. A decay rate of 10 to the negative 100 power per second would imply an average vacuum lifetime of 10 to the 100 power seconds, a time span that exceeds the current age of the universe by a factor of 10 to the 83rd power. Even if every atom in the observable universe were transformed into a clock ticking once per second, the combined ticking of all those clocks would not provide enough individual moments to measure such a time span. But vacuum decay calculations can yield actions much larger than 100, leading to lifetimes that surpass even these unimaginable timescales. Actions of several hundred or even 1,000 are not uncommon in realistic scenarios, corresponding to vacuum lifetimes measured in units where the age of the universe becomes vanishingly small by comparison. These are not approximate estimates or rough orders of magnitude. They are the inevitable mathematical consequences of applying well-established principles of quantum field theory to the problem of vacuum transitions. The extreme sensitivity of these calculations to small changes in input parameters creates both their power and their limitation. A modest change in the mass of the top quark, well within current experimental uncertainties, can shift the calculated tunneling action by tens or hundreds of units, changing the predicted vacuum lifetime by factors that involve more powers of 10 than there are atoms in the observable universe. This sensitivity means that improving the precision of particle mass measurements can dramatically refine our understanding of vacuum stability, but it also means that small theoretical uncertainties can lead to enormous differences in predicted outcomes. Perhaps the most unsettling aspect of vacuum lifetime calculations is their dependence on physics at energy scales, where our theoretical understanding becomes uncertain. The tunneling process that could trigger vacuum decay involves field configurations with energies approaching the Planck scale, the realm where quantum mechanics and general relativity merge into a theory of quantum gravity that we don't yet possess. At these energies, new physical effects might become important, effects that could either stabilize the vacuum against decay or accelerate the transition process in ways that our current theories cannot predict. This dependence on unknown high-energy physics introduces a fundamental uncertainty into all vacuum decay calculations. We can compute lifetimes with great precision using the standard model of particle physics, but we cannot guarantee that the standard model provides an accurate description of nature at the energy scales relevant to vacuum transitions. New particles, new forces, or new symmetries might modify the calculations in ways that are currently impossible to anticipate. What appears to be a metastable vacuum in the standard model might prove to be absolutely stable when additional physics is included, or conversely, additional interactions might reduce the barrier height and accelerate decay processes beyond current estimates. The phrase "longer than the age of the universe" appears frequently in discussions of vacuum decay, and it provides genuine reassurance about the immediate prospects for cosmic stability. But this phrase represents an inference based on current theoretical understanding, not a guarantee rooted in complete knowledge of fundamental physics. The calculations that yield these enormous lifetimes are mathematically rigorous within their domain of applicability, but that domain has boundaries, and we don't yet know exactly where those boundaries lie or what lies beyond them. When people first learn about vacuum decay and the possibility that our universe exists in a metastable state, a natural and deeply human question arises. Could we accidentally trigger it? Could the powerful particle accelerators that probe the fundamental structure of matter inadvertently provide the energy needed to nucleate a bubble of true vacuum? Could humanity, in its quest to understand the deepest layers of reality, inadvertently initiate the process that would rewrite the laws of physics and delete everything we know? This worry is not irrational or unscientific. It represents a legitimate concern that deserves serious analysis rather than dismissive reassurance. The fear stems from a reasonable intuition about energy and phase transitions. If vacuum decay requires overcoming an energy barrier, and if our particle accelerators are designed to concentrate enormous amounts of energy into tiny regions of space, then perhaps these machines could provide the energetic kick needed to push the Higgs field over the barrier that separates our current vacuum from a deeper one. The Large Hadron Collider, for instance, smashes protons together at energies of several trillion electron volts, creating conditions that haven't existed naturally since the earliest moments after the Big Bang. Could such collisions create the seed that grows into a bubble of cosmic destruction? Physicists have taken this concern seriously enough to conduct formal safety analyses, rigorous studies that apply our best theoretical understanding to the question of whether particle accelerators could pose existential risks. These analyses don't simply assert that danger is impossible. Instead, they work through the detailed physics of bubble nucleation, energy thresholds, and transition mechanisms to determine what level of risk, if any, might be associated with high-energy experiments. The first line of reasoning in these safety analyses involves a simple but powerful observation about the natural world. The universe has been conducting high-energy physics experiments for billions of years, experiments far more energetic than anything humanity has achieved or is likely to achieve in the foreseeable future. Cosmic rays, charged particles accelerated by magnetic fields around distant stars and black holes, routinely strike Earth's atmosphere with energies that dwarf those produced in our most powerful accelerators. Some cosmic ray particles carry energies of 10 to the 20th electron volts, or higher, millions of times greater than the maximum energies achievable at the Large Hadron Collider. These ultra-high energy cosmic rays don't simply pass through space harmlessly. They collide with nuclei in Earth's atmosphere, creating showers of secondary particles and concentrating enormous amounts of energy into extremely small volumes. If vacuum decay could be triggered by high-energy collisions, then the constant bombardment of cosmic rays over geological timescales would have provided countless opportunities for such events to occur. The fact that Earth, the solar system, and indeed our entire galaxy remain intact after billions of years of cosmic ray bombardment provides strong empirical evidence that high-energy collisions do not readily trigger vacuum decay. This cosmic ray argument extends beyond Earth to encompass the entire observable universe. Astronomical observations reveal that cosmic ray collisions occur throughout space, in the atmospheres of other planets, in the interstellar medium, and in the extreme environments surrounding neutron stars and black holes. Some of these environments expose matter to energy densities and collision rates that exceed terrestrial conditions by many orders of magnitude. Yet nowhere in the observable universe do we see evidence of the kind of expanding bubbles of altered spacetime that vacuum decay would produce. The theoretical analysis goes deeper than simple energy comparisons. Vacuum decay is not triggered simply by having a large amount of energy available in a collision. Instead, it requires very specific field configurations, arrangements where the Higgs field finds itself temporarily displaced, far from its usual value, and close to the barrier that separates different vacuum states. These configurations are extraordinarily improbable for several reasons that emerge from the detailed mathematics of quantum field theory. First, the energy required to displace the Higgs field significantly from its vacuum value is enormous, typically much larger than the total energy available in particle collisions, even at the highest energies we can achieve. Second, even if sufficient energy were available, it would need to be deposited in exactly the right way to create the field configuration that could evolve toward a vacuum transition. Random chaotic processes like particle collisions are remarkably inefficient at creating the highly organized, coherent field arrangements that bubble nucleation requires. The safety analyses conducted for particle accelerators also examined the specific mechanisms by which energetic collisions might, in principle, affect vacuum stability. These studies consider not just the total energy involved in collisions, but the detailed dynamics of how energy is transferred to quantum fields, how those fields respond to sudden disturbances, and how quickly any unusual configurations would decay back to normal vacuum fluctuations. The conclusion from these analyses is that artificially triggered vacuum decay is not merely unlikely, but requires conditions so extreme and specific that they lie far beyond the capabilities of any conceivable human technology. This doesn't mean that the concern about triggering vacuum decay is completely unfounded, or that it should be dismissed without careful consideration. Science advances by taking seriously even unlikely possibilities and subjecting them to rigorous analysis. The safety studies represent exactly this kind of careful, responsible approach to evaluating potential risks. They don't rely on intuition or authority, but on detailed calculations using our best current understanding of fundamental physics. However, these studies also reveal an important perspective on the relationship between human technology and cosmic processes. The energies we can achieve in our most powerful machines, impressive as they are by human standards, remain modest compared to the natural energy scales relevant to vacuum decay. The quantum restlessness of fields across cosmic space and time represents a far more significant source of potential vacuum transitions than any localized short-duration pulse of energy that human technology might produce. In the broader context of vacuum stability, the most realistic pathway to vacuum decay involves not sudden, dramatic triggering events, but the patient, probabilistic processes of quantum tunneling operating across vast expanses of space and time. If our vacuum is metastable, its ultimate fate will likely be determined by the subtle quantum fluctuations that probe all possible field configurations continuously throughout the universe, not by the brief energetic events that occur in particle accelerators or even in the most violent astrophysical phenomena. This perspective transforms the question from whether we might accidentally trigger vacuum decay to whether the universe will eventually experience such a transition through purely natural processes. The answer to that question depends not on human technology, but on the fundamental parameters of nature itself, parameters that we are still working to measure with the precision needed to make definitive predictions about cosmic stability. The story of vacuum stability cannot be told without venturing back to the earliest moments of cosmic history, to an epoch so remote and extreme that the very notion of stability takes on meanings far removed from our everyday experience. During the first fraction of a second after the Big Bang, the universe existed in conditions that would have challenged every assumption we make about the behavior of matter, energy, and space itself. It was during this primordial era, particularly during the period cosmologists call inflation, that questions about the Higgs field and vacuum stability would have been not merely theoretical curiosities, but immediate, practical concerns that could have determined whether a universe capable of supporting complexity would ever emerge. Inflation represents one of the most remarkable concepts in modern cosmology, a period of exponential expansion that occurred when the universe was less than a trillionth of a trillionth of a trillionth of a second old. During this brief but crucial epoch, the universe expanded by a factor that defies comfortable analogy. If a single atom were to expand by the same proportion, it would grow larger than a grapefruit. The space that would eventually contain our entire observable universe, with its billions of galaxies spanning 90 billion light-years, was once smaller than a subatomic particle. This extraordinary expansion was driven by the energy of quantum fields in highly unusual states, configurations far from the familiar vacuum conditions we observe today. The fields that filled space during inflation possessed enormous energy densities, sufficient to drive the exponential stretching of space-time itself. But inflation was not a perfectly smooth, uniform process. Like all physical systems, it was subject to quantum fluctuations, tiny random variations that arose from the fundamental uncertainty principles that govern quantum mechanics. Under normal circumstances, quantum fluctuations remain microscopic, confined to scales where their effects are detectable only through sophisticated experiments. But inflation changed this completely. The exponential expansion of space took quantum fluctuations that began smaller than atomic nuclei and stretched them to astronomical scales. Variations that started as quantum mechanical uncertainties became the seeds of cosmic structure. the tiny density differences that would eventually grow into galaxies, stars, and planets. The Higgs field, like all quantum fields, would have participated in this process. During inflation, the field would have experienced quantum fluctuations around its average value, random variations that were normally insignificant but became cosmically important due to the stretching effect of exponential expansion. These fluctuations meant that different regions of the early universe could have had slightly different values of the Higgs field, creating a patchwork of varying field strengths across space. Here is where the story of vacuum stability intersects with cosmology in a profound way. If the Higgs field exists in a metastable state today, with deeper vacuum states accessible through quantum tunneling, then during inflation, when the field experienced large fluctuations, some regions of space might have found themselves with field values much closer to, or even beyond, the barriers that separate different vacuum states. The violent quantum environment of the inflationary epoch could have provided exactly the kind of extreme field configurations that might trigger transitions to alternative vacuum states. This possibility transforms vacuum metastability from a concern about the distant future into a puzzle about the distant past. If our vacuum is truly metastable, if deeper energy states are accessible through quantum processes, then why didn't the extreme conditions of inflation drive transitions to these deeper states? Why do we observe a universe that appears to have settled into what might be only a temporarily stable configuration rather than the ultimate ground state of the Higgs potential? The fact that we exist, that we observe a universe filled with the kinds of complex structures that depend on the current masses of particles and strengths of forces, provides a powerful constraint on what could have happened during inflation. Our presence in the universe is not simply a stroke of cosmic luck, it's evidence about the physical processes that shape the early universe. If inflationary fluctuations had driven significant portions of space into alternative vacuum states, the resulting patchwork of different physics would likely have been incompatible with the formation of the large-scale structures we observe today. This line of reasoning suggests that either our vacuum is more stable than current calculations indicate, or that additional physics beyond the standard model provided mechanisms for stabilizing the Higgs field during the extreme conditions of inflation. Perhaps new particles or forces that become important only at very high energies help to anchor the field in its current configuration. Perhaps the dynamics of inflation itself created conditions that favored survival in the current vacuum state over transitions to alternatives. The early universe might have been protected by what cosmologists call the Hubble friction effect, a damping mechanism that arises from the rapid expansion of space during inflation. Just as ordinary friction can prevent a ball from rolling down a hill by dissipating its kinetic energy, Hubble friction can prevent quantum fields from evolving toward lower energy states by effectively increasing their apparent inertia. During inflation, this friction effect was enormously strong, potentially stabilizing field configurations that would be unstable under normal circumstances. Another possibility involves the detailed dynamics of how quantum fluctuations evolve during exponential expansion. The mathematical analysis of field evolution during inflation is extraordinarily complex, involving the interplay between quantum mechanics, general relativity, and the unusual thermodynamic properties of exponentially expanding space. Some calculations suggest that fluctuations large enough to drive vacuum transitions might be exponentially suppressed during inflation, making dangerous field excursions much less likely than naive estimates would suggest. The mystery deepens when you consider that inflation itself had to end somehow. The exponential expansion could not continue forever, or we would not observe the universe we see today. The transition from inflation to the more familiar expansion of the standard Big Bang model required the fields driving inflation to decay, to give up their enormous energy and settle into configurations compatible with ordinary matter and radiation. This transition, known as reheating, involved precisely the kind of dramatic field evolution that could, in principle, have triggered vacuum decay if our vacuum is indeed metastable. The survival of our universe through the inflationary epoch and the subsequent reheating process provides one of the most stringent tests of vacuum stability that nature has ever conducted. The extreme energies, violent fluctuations, and dramatic field transitions of the early universe created conditions far more challenging than anything our particle accelerators can achieve, or anything likely to occur in the cosmic future. If the Higgs field could navigate this gauntlet without making transitions to alternative vacuum states, it suggests either remarkable stability or remarkable luck, or perhaps physical mechanisms we don't yet understand that provided protection during this crucial epoch. In the theoretical landscape of vacuum decay, physicists have identified not one but two distinct pathways by which a metastable vacuum might make the transition to a lower energy state. These pathways represent fundamentally different mechanisms, each operating under its own set of conditions and each leading to dramatically different scenarios for how the transition might unfold across space and time. Understanding both mechanisms is crucial to grasping the full complexity of vacuum stability, because the pathway that dominates depends on the precise cosmological environment in which the transition occurs. The first pathway, which we have already explored in detail, is the Coleman-de Lucia mechanism, named after the physicists who developed its mathematical framework in the 1970s and 80s. This mechanism describes what we might call a localized transition, where a small region of space spontaneously nucleates a bubble of true vacuum through quantum tunneling. The bubble forms at a specific location and time, creating a sharp boundary between the new vacuum state inside and the old vacuum state outside. Once formed above the critical size, this bubble expands outward, its wall accelerating toward the speed of light as it consumes more and more of the surrounding false vacuum. The Coleman-de Lucia process has an intuitive appeal because it resembles familiar phase transitions in everyday experience. When water boils, bubbles of vapor form at specific locations in mind, the liquid, and then expand until the entire volume has transitioned to the gaseous state. When a supercooled liquid finally freezes, crystallization often begins at particular nucleation sites and spreads throughout the material. The Coleman-de Lucia mechanism applies similar logic to the fabric of space-time itself, describing how a new phase of vacuum can nucleate and spread through the universe. But there exists a second, more subtle pathway for vacuum decay, one that operates according to very different principles. The Hawking-Moss mechanism, developed by Stephen Hawking and Ian Moss, describes a more global form of transition that can occur when the universe undergoes a period of exponential expansion, such as during cosmic inflation or in the presence of a cosmological constant. Rather than forming localized bubbles, the Hawking-Moss process involves a coherent transition of large regions of space simultaneously over the energy barrier that separates different vacuum states. To understand the Hawking-Moss mechanism, you need to appreciate how the expansion of space itself affects the dynamics of quantum fields. In a rapidly expanding universe, the stretching of spacetime creates an environment that is thermodynamically similar to a system at finite temperature. This effective temperature is determined by the rate of expansion, and it can be high enough to provide quantum fields with the thermal energy needed to hop over barriers that would be insurmountable in static spacetime. Think of the difference between the two mechanisms this way. The Coleman-de Lucia process is like a marble that tunnels through the wall of its cup and begins rolling down the hillside toward a lower valley. The transition starts at a specific point and spreads outward from there. The Hawking-Moss process is more like the entire landscape being shaken so vigorously that the marble is jostled over the rim of its cup, not through tunneling, but through thermal fluctuations induced by the shaking itself. The end result is the same, a transition to a lower energy state, but the mechanism is fundamentally different. The choice between these two pathways depends critically on the cosmological context in which the vacuum finds itself. In a universe that is static or expanding slowly, the Coleman-de Lucia mechanism typically dominates. The effective temperature induced by expansion is low, thermal effects are negligible, and vacuum transitions must occur through the quantum tunneling of localized regions. But in a rapidly expanding universe, particularly one undergoing exponential inflation, the Hawking-Moss mechanism can become the dominant process. The effective temperature rises with the expansion rate, and thermal hopping over barriers can become more probable than tunneling through them. This cosmological dependence adds another layer of complexity to questions about vacuum stability. It's not sufficient to calculate tunneling rates and bubble formation probabilities in flat spacetime. You must also consider how these rates change in the curved, expanding spacetime that characterizes our actual universe. The cosmological constant, which drives the current accelerated expansion of space, creates precisely the kind of environment where Hawking-Moss transitions might become important, particularly if the acceleration continues to increase over cosmic time. The mathematical analysis of both mechanisms requires sophisticated techniques that combine quantum field theory with general relativity. For Coleman-de Lucia bubbles, you must solve the equations that describe how field configurations evolve in curved spacetime, taking into account both the quantum tunneling process and the gravitational effects of the energy concentrated in the bubble wall. For Hawking-Moss transitions, you must analyze how thermal fluctuations in curved spacetime can drive fields over energy barriers, a calculation that involves the subtle interplay between quantum mechanics and thermodynamics in expanding universes. What makes this analysis particularly challenging is that the two mechanisms can compete with each other under certain circumstances. In some cosmological environments, both pathways might be possible, with the dominant mechanism determined by which process has the higher probability rate. Small changes in the expansion rate, the height of energy barriers, or the curvature of spacetime can tip the balance from one mechanism to the other, leading to very different predictions about how vacuum decay might unfold. The existence of multiple pathways for vacuum decay also affects the observational signatures that such transitions might produce. Coleman-de Lucia bubbles create sharp boundaries in spacetime where the laws of physics change discontinuously. These boundaries might, in principle, be detectable through their gravitational effects or their influence on the cosmic microwave background radiation. Hawking-Moss transitions, by contrast, tend to produce more gradual global changes that might be harder to distinguish from other cosmological processes. Perhaps most importantly, the recognition that vacuum decay can proceed through multiple mechanisms emphasizes the sophistication required to make reliable predictions about cosmic stability. It's not enough to calculate a single decay rate and declare the vacuum stable or unstable. You must consider the full spectrum of possible transition mechanisms, each operating under its own conditions, each contributing to the total probability of vacuum decay. The universe, it seems, provides multiple exits from any metastable state, and determining which exit might be used requires understanding the detailed interplay between quantum mechanics, field theory, and cosmology. This multiplicity of mechanisms doesn't increase the danger of vacuum decay, but it does increase the complexity of the calculations needed to assess that danger accurately. It reminds us that the universe operates according to principles that are both more subtle and more varied than our everyday intuitions might suggest. If you could witness a bubble of true vacuum expanding through space, the most remarkable feature you would observe would not be the bubble interior or the undisturbed exterior, but the boundary itself, the thin shell of space-time where one set of physical laws gives way to another. This boundary, which physicists call the bubble wall, represents one of the most profound transitions imaginable, a region where the fundamental constants that define reality are in the process of changing from one set of values to another. It is, quite literally, a place where the rules of physics are being rewritten in real time. To understand what this means, you need to appreciate that the constants of nature are not arbitrary numbers that physicists have assigned to make their equations work. They are not decorative parameters or convenient mathematical tools that could be adjusted at will without consequence. The fundamental constants determine what kinds of particles can exist, what masses those particles have, how strongly they interact with each other, and what kinds of structures those interactions can create and sustain. They are the deep grammar of physical reality, the underlying syntax that makes the complex sentences of atoms, molecules, chemistry, and life possible. When we speak of the mass of an electron, we are not describing some intrinsic property that the electron possesses independently of everything else in the universe. We are describing how strongly that particle couples to the background Higgs field that fills all of space. Change the value of the Higgs field, and you change the mass of the electron. Change it dramatically, and you might eliminate the electron's mass entirely, transforming it into a massless particle that travels at the speed of light and can no longer be bound into atoms. The same principle applies to every massive particle in the standard model of physics, from quarks to leptons to the force-carrying bosons that mediate interactions between them. The bubble wall represents a region where the Higgs field is in transition from its current value, which we observe throughout our universe, to whatever value it would have in the true vacuum state. As the field rolls from one configuration to another, the masses of particles change continuously across the wall. Near the outer edge, where the field value remains close to its familiar form, physics operates according to the rules we know. Near the inner edge, where the field approaches its new equilibrium, physics begins to operate according to rules that could be radically different from anything we have observed. But particle masses are just the beginning of the story. The strength of the fundamental forces also depends on the background values of quantum fields, including the Higgs field. Change those background values, and you change how strongly protons and neutrons bind together in atomic nuclei, how tightly electrons are held in their atomic orbits, and how readily atoms combine to form molecules. These are not minor adjustments that might make chemistry slightly different or nuclear physics marginally more interesting. They are changes that could eliminate the very possibility of complex structures existing at all. Consider what happens to an atom if the mass of the electron changes dramatically as it encounters the bubble wall. The size of atomic orbitals, the energy levels of electronic states, and the stability of chemical bonds all depend precisely on the electron's mass. Make the electron significantly heavier, and atoms shrink to sizes where nuclear and electronic wave functions begin to overlap in ways that our current understanding of chemistry cannot accommodate. Make the electron massless, and atoms cease to exist entirely, as the electron becomes unable to maintain bound states with nuclei. The situation becomes even more complex when you consider the strong nuclear force, which holds protons and neutrons together inside atomic nuclei. This force is mediated by particles whose masses and interactions are determined by the same Higgs mechanism that gives mass to electrons and quarks. Change the Higgs field value, and you change the balance between the attractive strong force and the repulsive electromagnetic force that operates between protons. Shift this balance even slightly, and you could eliminate the possibility of stable nuclei, making it impossible for atoms heavier than hydrogen to exist. What emerges from this analysis is a picture of matter as we know it existing within a narrow range of parameter space defined by the current values of fundamental constants. The atoms that make up your body, the molecules that enable the chemistry of life, the nuclear reactions that power the stars, all depend on a precise coordination between particle masses, force strengths, and interaction rates that arise from the current configuration of quantum fields. Change that configuration significantly, and the scaffolding that supports complex structures throughout the universe begins to collapse. But here we must acknowledge a fundamental limitation in our ability to predict what would actually happen inside a bubble of true vacuum. We can outline categories of change and identify the physical principles that would be violated, but we cannot provide a detailed inventory of what the post-transition universe would look like. The new values of fundamental constants would depend on the precise shape of the Higgs potential at high energies, information that we cannot extract from current measurements and that might depend on physics beyond the standard model. It's possible that the true vacuum represents a configuration where complex structures could exist, just different ones operating according to different rules. Perhaps new forms of matter could emerge, bound together by forces that are weak or absent in our current vacuum but dominant in the true vacuum state. Perhaps the apparent hostility of the new physics to familiar forms of matter masks the possibility of exotic forms of organization that we cannot currently imagine. Alternatively, the true vacuum might represent a configuration that is genuinely inhospitable to complexity of any kind. The field values that minimize energy might correspond to a universe where all particles are massless, where forces are too weak to bind anything together, or where the basic requirements for structure formation are simply absent. Such a universe might consist of nothing but light and other massless particles racing through empty space at the speed of light, forever unable to slow down, combine, or create the kinds of persistent patterns that we associate with interesting physics. The bubble wall thus represents not just a boundary between different regions of space, but a boundary between different possibilities for what kinds of universes can exist. As it expands outward at nearly the speed of light, it carries with it the power to determine which of these possibilities becomes reality, rewriting the fundamental laws that govern everything from subatomic interactions to the formation of galaxies. Step across the threshold of a true vacuum bubble, and you enter a realm where the phrase "atoms cease to exist" takes on a meaning far more precise and unsettling than everyday language can easily accommodate. This is not the dramatic deletion of science fiction, not the sudden vanishing of matter in a flash of light or energy. This is something both more subtle and more complete. The elimination of the very possibility that atoms can form stable, bound states under the altered rules of physics that govern the bubble interior. To understand what this means, you need to think about what an atom actually is in terms of fundamental physics. An atom is not a miniature solar system with electrons orbiting a central nucleus, despite the persistent appeal of that early 20th century model. An atom is a quantum mechanical bound state, a stable configuration of particles held together by forces that are precisely balanced to create long-lived structures capable of participating in the complex interactions we call chemistry. The existence of atoms depends on a delicate coordination between the masses of electrons and quarks, the strength of electromagnetic and nuclear forces, and the quantum mechanical rules that govern how particles can arrange themselves in space. Change any of these parameters significantly, and the balance that makes atoms possible begins to collapse. If electrons become too heavy, atomic orbitals shrink until quantum mechanical effects prevent stable bound states from forming. If electrons become too light, or worse, massless, they can no longer be captured and held by nuclear charges, racing away at the speed of light instead of settling into the energy levels that make chemistry possible. If the strong nuclear force becomes too weak, protons and neutrons cannot bind together to form stable nuclei. If it becomes too strong, the electromagnetic repulsion between protons is overwhelmed, leading to nuclear configurations that bear no resemblance to the periodic table we know. Inside a true vacuum bubble, where the Higgs field has settled into its lowest possible energy state, the fundamental constants that govern these interactions could take on values radically different from those we observe in our current vacuum. The new values would not be chosen randomly or maliciously. They would be determined by the same principles of energy minimization that govern all physical systems, but operating under conditions we have never observed and cannot directly probe with our current experimental techniques. Some theoretical analyses suggest that the true vacuum state might correspond to a space-time geometry known as anti-de Sitter space, a curved space-time with properties fundamentally different from the nearly flat geometry we observe in our universe. Anti-de Sitter space has a negative cosmological constant, creating a gravitational environment where distances and times evolve according to hyperbolic rather than Euclidean geometry. In such a space, the very notion of stable matter configurations might become meaningless, not because matter is actively destroyed, but because the underlying geometry of space-time makes the kinds of bound states we call atoms energetically impossible. But we must be careful not to overstate our understanding of what lies beyond the boundary of our current vacuum. The calculations that predict these exotic outcomes are based on extrapolations of the standard model to energy scales and field values far beyond the realm of experimental verification. We are using equations derived from physics we can measure to make predictions about physics we have never observed. This extrapolation, however mathematically rigorous, carries uncertainties that compound as we venture further from known territory. Physics beyond the standard model might provide mechanisms that stabilize familiar forms of matter, even in the true vacuum state. New particles or forces that become important only at very high energies might create opportunities for complex structures that operate according to principles we haven't yet discovered. The true vacuum might not represent a sterile environment hostile to all forms of organization, but rather a different kind of fertile ground where exotic forms of matter and energy can flourish according to rules that transcend our current theoretical framework. Alternatively, the true vacuum might represent something even stranger than the elimination of atoms, the emergence of entirely new categories of physical phenomena that have no analogue in our current experience. Just as the transition from classical to quantum mechanics revealed forms of behavior that classical physics could not anticipate, the transition to a true vacuum state might unveil aspects of nature that our current theories cannot even formulate as possibilities. We might be attempting to describe the interior of the bubble using conceptual tools that are fundamentally inadequate for the task. This uncertainty extends to the very meaning of concepts like space, time, and causality inside the bubble. If the true vacuum corresponds to a dramatically different space-time geometry, then questions about what kinds of structures can exist become questions about what kinds of structures the concepts of existence and structure can even accommodate. We find ourselves at the boundaries not just of current knowledge but of current language, attempting to describe transformations so fundamental that they challenge the basic categories through which we understand physical reality. Yet even as we contemplate these exotic possibilities, we cannot escape a profound appreciation for the extraordinary hospitability of our present vacuum state. Whatever the true ground state of the Higgs potential might be, whatever forms of matter and energy might flourish in alternative vacuum configurations, our current state has proven remarkably conducive to the emergence and maintenance of complex structures. The particular values of fundamental constants we observe have allowed hydrogen and helium to form in the early universe, heavier elements to be forged in stellar cores, planets to condense from primordial gas clouds, and chemistry to develop the intricate molecular choreography that makes biological processes possible. The atoms that compose your body, the molecules that enable your thoughts, the nuclear reactions that warm the Earth, all exist within a narrow range of parameter space where the fundamental forces achieve exactly the kind of balance needed to support persistent, complex, evolving structures. Whether this represents an absolute minimum of energy or merely a local depression in a larger landscape, it has nonetheless provided a foundation stable enough to support billions of years of cosmic evolution, stellar formation, planetary development, and the emergence of life capable of contemplating its own physical foundations. The bubble interior might represent the ultimate destination toward which our universe is slowly evolving, or it might represent an alternative that will never be realized. But our present vacuum, whatever its ultimate fate, has already demonstrated its capacity to host the most remarkable phenomenon we know, the emergence of matter capable of understanding the very laws that govern its existence. The story of vacuum stability takes on an entirely different character when you step back from the specific details of the Higgs field and particle masses to consider a broader question that has emerged from decades of theoretical research in fundamental physics. What if our universe, with its particular vacuum state and specific values of fundamental constants, represents not a unique solution to the equations that govern reality, but merely one possibility among an enormous number of alternatives? What if the deepest theories of nature allow for countless different ways that quantum fields can settle into stable or metastable configurations, each giving rise to universes with their own distinct properties and physical laws? This possibility, known among physicists as the landscape scenario, transforms questions about vacuum stability from puzzles about our specific cosmic environment into explorations of a vast space of theoretical possibilities. In this view, the metastability that might characterize our vacuum becomes not an unusual or problematic feature requiring special explanation, but a natural and expected property of most regions in a landscape populated by numerous vacuum states. The landscape concept provides a conceptual framework within which metastability appears not as an accident or flaw in the design of our universe, but as an inevitable consequence of the rich mathematical structure of fundamental physics. The roots of the landscape idea extend deep into string theory, the ambitious attempt to describe all fundamental particles and forces as different vibrational modes of tiny one-dimensional objects called strings. String theory, in its various formulations, appears to allow for an enormous number of different vacuum states, each corresponding to different ways that extraspatial dimensions can be compactified, different ways that strings can wrap around topological features of those dimensions, and different ways that the various fields in the theory can settle into equilibrium configurations. Early estimates suggested that the number of possible vacuum states in string theory might reach 10 to the 500th power or higher, a number so large that it defies any attempt at comprehensive cataloguing or systematic exploration. Each of these vacuum states would correspond to a different set of physical laws, different masses for fundamental particles, different strengths for the forces that govern their interactions, and different values for the constants that determine everything from the stability of atoms to the rate of cosmic expansion. Some of these states might support rich, complex physics similar to what we observe in our universe. Others might be so different from our experience that familiar concepts like matter, energy, and even space and time would take on meanings that we cannot currently anticipate or understand. In the context of such a landscape, our particular vacuum state would represent just one point in an enormous space of possibilities. The specific values of the Higgs mass, the top quark mass, and the other parameters that determine whether our vacuum is stable or metastable would be features of our local environment rather than fundamental properties of reality itself. Other regions of the landscape might contain vacuum states that are absolutely stable, immune to any form of decay or transition. Still others might be so unstable that they could never persist long enough for complex structures to develop. This perspective offers a potential resolution to what physicists call the fine-tuning problem, the observation that many of the constants of nature, appear to be precisely adjusted to values that allow for the existence of stars, planets, chemistry, and life. Rather than requiring some mechanism that sets these constants to their observed values with extraordinary precision, the landscape scenario suggests that all possible values are realized somewhere in the vast space of vacuum states. We observe the particular values we do simply because they are the ones that exist in our local region of the landscape, and we exist in this region because it is one of the relatively rare areas where the conditions are hospitable to the formation of complex, self-aware structures. But the landscape concept comes with significant caveats that prevent it from being a complete or entirely satisfying explanation for the properties of our universe. First and most importantly, the landscape remains largely conjectural. String theory, despite decades of intensive research, has not yet made contact with experimental observation in a way that would allow definitive tests of its predictions. The existence of the vast number of vacuum states that the landscape requires has not been established through direct calculation or observational evidence. It remains a theoretical possibility rather than a confirmed feature of reality. Moreover, even if the landscape exists, it does not necessarily provide a mechanism for transitions between different vacuum states. The various regions of the landscape might be isolated from each other by energy barriers so high that transitions between them are effectively impossible, even over cosmic timescales. In such a scenario, the landscape would represent a catalogue of theoretical possibilities rather than a description of accessible physical states. Our vacuum might be metastable relative to other states in the landscape, but if those states are unreachable through any physical process, the metastability becomes irrelevant for practical purposes. The landscape also raises profound questions about the nature of scientific explanation and prediction. If every possible set of physical laws is realized somewhere in the landscape, then the specific properties we observe in our universe become accidents of cosmic geography rather than consequences of fundamental principles. This might resolve certain puzzles about fine-tuning, but it also eliminates the possibility of deriving the observed properties of nature from deeper theoretical principles. Science would become less about understanding why the universe has the properties it does, and more about mapping which regions of the landscape are capable of supporting observers. Despite these limitations, the landscape concept provides valuable perspective on questions of vacuum stability by demonstrating that metastability need not be viewed as an unusual or problematic feature of our universe. In a theoretical framework that allows for vast numbers of vacuum states, most states would naturally be metastable, separated from other configurations by finite energy barriers that could, in principle, be overcome through quantum tunneling or thermal fluctuations. Absolute stability would be the exception rather than the rule, achieved only in special regions of the landscape where no lower energy states are accessible. This broader context does not eliminate concerns about vacuum decay or resolve questions about the ultimate fate of our universe. But it does place those concerns within a richer conceptual framework that makes metastability appear less like a cosmic accident and more like a natural feature of the complex mathematical structures that might underlie fundamental physics. The question of whether our universe exists in a state of ultimate stability or merely temporary equilibrium is not destined to remain forever in the realm of theoretical speculation. Science, with its relentless drive toward greater precision and deeper understanding, is steadily transforming this cosmic puzzle from a matter of philosophical contemplation into a problem that can be approached through measurement, calculation, and systematic investigation. The tools and techniques that will determine the fate of our vacuum are being developed and refined in laboratories around the world, each incremental improvement bringing us closer to a definitive answer about the ultimate stability of everything we know. The path toward understanding lies primarily through improved measurements of the fundamental parameters that govern the evolution of the Higgs potential at high energies. Every decimal place of precision gained in our knowledge of particle masses, every refinement in our understanding of how coupling constants change with energy, every reduction in the systematic uncertainties that affect our calculations contributes to a clearer picture of where our vacuum sits in the landscape of theoretical possibilities. The difference between absolute stability and metastability, as we have seen, can hinge on changes in measured parameters that are smaller than current experimental uncertainties, making precision measurement not just useful, but essential for resolving these questions. The mass of the top quark remains one of the most crucial parameters in this endeavour. Its enormous influence on the evolution of the Higgs coupling through quantum loop corrections means that even small improvements in our knowledge of its value can dramatically sharpen our conclusions about vacuum stability. Current measurements place this mass at approximately 173 billion electron volts, but the experimental collaborations working at the Large Hadron Collider continue to refine this number through increasingly sophisticated analysis techniques. Each new dataset, each improvement in detector calibration, each advance in theoretical understanding of how to extract particle masses from collision data contributes to a more precise determination of this critical parameter. The Higgs boson mass itself has become one of the most precisely measured quantities in all of particle physics, a remarkable achievement considering that the particle was only discovered in 2012. The combined efforts of the ATLAS and CMS experimental collaborations have determined this mass to an accuracy approaching 1 part in 1,000, a level of precision that allows meaningful extrapolations to energy scales trillions of times higher than anything we can produce directly in our accelerators. This precision represents the culmination of decades of technological development, from the superconducting magnets that guide particle beams through underground tunnels to the silicon detectors that track the paths of individual particles through complex electromagnetic fields. But measurement precision is only half of the story. Equally important are the theoretical developments that allow us to translate experimental measurements into reliable predictions about vacuum stability. The quantum field theory calculations that describe how coupling constants evolve with energy have become increasingly sophisticated, incorporating higher-order corrections that account for ever more subtle effects. These calculations now routinely include contributions that would have been considered impossibly complex just a generation ago, effects involving multiple quantum loops, intricate cancellations between different physical processes, and the influence of virtual particles that exist for timescales so brief that they cannot be observed directly. The future of vacuum stability research is being shaped by a new generation of experimental facilities designed to push precision measurements even further beyond current capabilities. The High Luminosity Large Hadron Collider, scheduled to begin operation later in this decade, will collect datasets 100 times larger than those currently available, providing unprecedented statistical power for measuring rare processes and extracting subtle signals from enormous backgrounds of ordinary particle interactions. This facility will allow physicists to probe aspects of Higgs physics that are currently inaccessible, including rare decay modes, precise measurements of how the Higgs couples to different particles, and detailed studies of how these couplings change under different conditions. Beyond traditional particle acceleration experiments, computational physics has emerged as a crucial tool for understanding vacuum stability. Advanced computer simulations now allow researchers to model the formation and evolution of vacuum bubbles, exploring how these structures might nucleate, grow, and interact with each other in realistic cosmological environments. These simulations provide insights that cannot be obtained through analytical calculations alone, revealing the complex dynamics of field evolution in curved space-time and the subtle interplay between quantum tunneling and gravitational effects. The computational requirements for these simulations push the boundaries of high-performance computing, utilizing some of the world's most powerful supercomputers to solve equations that describe the behavior of quantum fields across vast ranges of energy and distance scales. Perhaps most remarkably, the question of vacuum stability has evolved from an abstract theoretical curiosity into an active area of observational cosmology. Researchers are developing techniques to search for the signatures that vacuum bubbles would leave in the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe with a faint but detectable glow. If vacuum decay has occurred anywhere in the observable universe since the cosmic microwave background was formed, it might have left subtle distortions in this radiation that could be detected by current or future space-based telescopes. These searches represent an extraordinary fusion of theoretical physics and observational astronomy, using measurements of ancient light to probe questions about the fundamental stability of space-time itself. The steady accumulation of experimental data and theoretical understanding has created a sense of controlled progress toward answering one of the deepest questions in all of physics. We may still be years or decades away from a definitive resolution of vacuum stability, but we are no longer in the realm of pure speculation. The mathematical framework exists, the experimental techniques are being refined, and the measurements needed to resolve the question are gradually becoming available with the precision required to matter. This transformation from philosophical puzzle to measurable physical phenomenon represents one of the great achievements of modern science. The universe's stability is slowly but surely becoming a question that can be answered through observation and calculation rather than speculation and debate. Whatever that answer turns out to be, the process of finding it demonstrates the extraordinary power of human ingenuity applied to understanding the deepest foundations of reality itself. When you contemplate the possibility of vacuum decay, it's natural for your mind to leap immediately to questions of timing, to wonder whether such an event might occur tomorrow, next year, or within your lifetime. This temporal anxiety reflects a deeply human tendency to think about rare events in terms of personal schedules and familiar timescales. But vacuum decay, if it occurs at all, operates according to a fundamentally different relationship with time, one that can transform initial feelings of cosmic dread into a profound appreciation for the scales on which the universe actually operates. The best way to understand the temporal character of vacuum decay is to think about radioactive decay, a process that shares the same mathematical structure but operates on scales we can observe and measure directly. When you hold a sample of radioactive material, you cannot predict when any individual atom will decay. Each atom has exactly the same probability of decaying in the next second, regardless of whether it formed moments ago or has existed for billions of years. Radioactive atoms do not age in any meaningful sense. They do not accumulate damage, wear down over time, or become more likely to decay simply because they have persisted for a long period. This timeless quality of quantum decay processes means that a radioactive atom that has survived for 1,000,000 years is no more likely to decay in the next second than an atom that formed yesterday. The probability remains constant, independent of history, independent of duration, independent of any notion of accumulated stress or fatigue. Each moment represents a fresh statistical trial with the same odds as every moment that came before and every moment that will come after. Vacuum decay follows exactly the same statistical principles, but applied to the fabric of space-time itself rather than to individual atomic nuclei. If our vacuum is metastable, then each region of space has a tiny, constant probability per unit time of spontaneously nucleating a bubble of true vacuum. This probability does not increase with the age of the universe. It does not accumulate over time like interest in a bank account. it does not build up pressure that makes vacuum decay more likely as cosmic time progresses. Each moment in cosmic history represents an independent trial, with the same extraordinarily small probability of transition that has characterized every moment since the universe began. This perspective offers a form of comfort that emerges directly from understanding the mathematics of probability. The fact that the universe has already existed for nearly 14 billion years without experiencing vacuum decay does not mean that such an event is now overdue, or that the odds are somehow building against us. Each year that passes, each billion years of cosmic evolution, each era of stellar formation and galactic merger represents not an accumulation of risk, but simply another sequence of independent trials, each with the same negligible probability of producing a vacuum transition. To appreciate what this means in practical terms, consider the difference between human timescales and cosmic timescales. A human lifetime spans roughly 70 years, a duration that seems substantial from our personal perspective, but represents only 5 billionths of the current age of the universe. Even if vacuum decay were destined to occur at some point in the cosmic future, the probability that it would happen during your specific lifetime, during your particular several decades out of the trillions of years that the universe might exist, would be vanishingly small. But the comfort of scale extends far beyond personal lifetimes to encompass the entire future of human civilization, the evolution of our solar system, and the life cycle of our galaxy. Current estimates suggest that the Sun will continue to burn hydrogen for another 5 billion years before exhausting its core fuel and evolving into a red giant star. The Milky Way galaxy will continue to form new stars from interstellar gas for trillions of years to come, until the expansion of the universe spreads matter so thin that stellar formation can no longer continue. Even after the last stars burn out, protons themselves might decay over timescales measured in 10 to the 34th power years or longer, gradually dissolving the atomic structures that compose planets, asteroids, and the cold remnants of dead stars. All of these immense timescales, from the future evolution of our Sun to the potential decay of matter itself, unfold against the backdrop of vacuum decay probabilities so extraordinarily small that they make even these cosmic timescales appear brief by comparison. The theoretical calculations that predict vacuum lifetimes often yield numbers with exponents in the hundreds or thousands, timescales so vast that the entire future history of stellar evolution becomes a negligible blip in the overall story of cosmic time. This is not to say that vacuum decay is impossible, or that we can dismiss it as irrelevant to the ultimate fate of the universe. The mathematics of quantum mechanics guarantees that any process with a non-zero probability will eventually occur if given sufficient time and opportunity. But the timescales involved are so enormous that they transcend not just human experience, but human conceptual frameworks for thinking about duration and permanence. Perhaps most remarkably, the universe has already provided us with powerful empirical evidence for the extraordinary stability of our vacuum state. The fact that complex structures exist throughout the observable universe, that stars have been forming and dying for billions of years, that galaxies have assembled and evolved over cosmic time, all testify to the remarkable persistence of the physical laws and fundamental constants that govern reality. Whatever the ultimate fate of our vacuum might be, it has already demonstrated a stability and reliability that spans the entire history of cosmic evolution. This empirical track record does not guarantee eternal stability, but it does provide a foundation for confidence that transcends theoretical calculations and probability estimates. Our vacuum has proven itself capable of supporting the formation of stars, the synthesis of heavy elements, the condensation of planets, and the emergence of life complex enough to contemplate its own physical foundations. It has maintained the precise balance of forces and constants needed for chemistry to operate, for nuclear physics to create the elements that compose our world, and for electromagnetic interactions to enable the intricate molecular processes that make biological systems possible. The deepest comfort in contemplating vacuum stability comes not from dismissing the possibility of decay, but from appreciating the extraordinary achievement represented by our current cosmic state. Whether temporary or eternal, metastable or absolutely stable, our vacuum has provided a foundation reliable enough to support the most remarkable phenomenon we know: the emergence of matter capable of understanding the very principles that govern its own existence. There exists a profound paradox at the heart of our universe that challenges our most basic intuitions about stability and fragility. On one hand, if current theoretical calculations are correct, we may inhabit a cosmos whose fundamental vacuum state represents not the absolute ground floor of physical reality, but merely a temporary resting place, a cosmic way station that could theoretically give way to deeper, more stable configurations. On the other hand, this potentially fragile foundation has already supported nearly 14 billion years of uninterrupted cosmic evolution, stellar formation, galactic assembly, and the emergence of complexity on scales ranging from molecular chemistry to biological consciousness. These two perspectives seem to contradict each other until you realize that they are both expressions of the same underlying physics, two faces of quantum mechanics operating across the vast scales of space and time that characterize our universe. The apparent contradiction dissolves when you appreciate that metastability in quantum systems can coexist with extraordinary longevity in ways that have no analogue in everyday experience. Consider a quantum state that exists in a local energy minimum, separated from deeper minima by barriers that are high and wide enough to suppress transitions for timescales that exceed the current age of the universe by factors measured in tens or hundreds of orders of magnitude. Such a state is simultaneously metastable, in the sense that lower energy configurations exist in principle, and stable, in the sense that transitions to those configurations are so improbable that they may never occur during the entire future history of cosmic evolution. This is not a theoretical curiosity, but a fundamental feature of how quantum mechanics operates at macroscopic scales. The same mathematical principles that allow individual radioactive nuclei to remain unchanged for billions of years while retaining a finite probability of decay also allow entire vacuum states to persist for timescales that dwarf the age of galaxies while remaining technically subject to eventual transition. The physics that permits instability also generates the extraordinary suppression factors that make that instability irrelevant for all practical purposes. What makes this duality particularly striking is that it emerges from the most precise and well-tested theory in all of physics. Quantum mechanics is not a speculative framework or an approximation valid only under limited conditions. It is the mathematical foundation that underlies our understanding of atoms, molecules, chemistry, nuclear physics, and particle interactions. Every prediction it makes about the behavior of matter and energy has been verified to extraordinary precision through decades of experimental investigation. When quantum mechanics tells us that metastable states can persist for unimaginably long periods while retaining the theoretical possibility of decay, we are not dealing with conjecture, but with the established consequences of our most successful physical theory. This perspective transforms the relationship between fragility and durability from a contradiction into a complement. The very quantum mechanical principles that introduce the possibility of vacuum decay through tunneling processes also generate the exponential suppression factors that make such decay effectively impossible over human, geological, or even astronomical timescales. The universe is not fragile despite being potentially metastable. It achieves its remarkable durability precisely through the mechanisms that make metastability possible. The mathematical elegance of this relationship reveals something profound about the architecture of physical law. Nature has arranged itself in such a way that stability does not require absolute permanence, and impermanence does not imply immediate vulnerability. Instead, the universe operates in a regime where extraordinary longevity can emerge from finite transition probabilities, where cosmic robustness can coexist with theoretical mutability, and where the possibility of change enables rather than threatens the persistence of complex structures over cosmic time. This insight extends far beyond questions of vacuum stability to illuminate the nature of persistence and change throughout the physical world. Stars burn for billions of years while gradually consuming their nuclear fuel. Galaxies maintain their spiral structure while continuously exchanging matter with their surroundings. Even living organisms persist as recognizable entities while constantly replacing their constituent molecules through metabolism and growth. In each case, apparent permanence emerges not from absolute stasis, but from dynamic processes that maintain stable patterns while allowing for underlying change. Our universe, viewed from this perspective, reveals itself as a masterwork of balanced impermanence. Every structure we observe, from subatomic particles to galactic clusters, exists in states that are simultaneously stable enough to support complex organization and dynamic enough to permit evolution and development. The fundamental constants that govern physics maintain values that have remained unchanged throughout cosmic history, while arising from field configurations that could, in principle, evolve toward different equilibrium states. The laws of nature themselves exhibit the same paradoxical combination of reliability and theoretical mutability that characterizes individual quantum systems. Perhaps most remarkably, this cosmic balance has proven capable of supporting the emergence of structures complex enough to contemplate their own foundations. The universe has not merely persisted through billions of years of cosmic evolution. It has done so while fostering increasingly sophisticated forms of organization, from the first hydrogen and helium nuclei formed in the early universe to the intricate molecular machinery that enables biological processes to the neural networks that make conscious thought possible. The extraordinary nature of this achievement becomes clear when you consider how narrow the range of physical conditions must be to permit such complexity. Slight changes in the masses of fundamental particles would prevent atoms from forming. Small adjustments to the strengths of nuclear forces would eliminate the possibility of stable elements heavier than hydrogen. Minor alterations in the electromagnetic interaction would disrupt the chemical bonds that make molecular structures possible. Our universe exists in a region of parameter space where all of these requirements are simultaneously satisfied, and it has maintained this delicate balance throughout the entire history of cosmic evolution. This balance between fragility and durability invites not anxiety about cosmic instability, but awe at cosmic achievement. Whether our vacuum represents the absolute ground state of reality, or merely a long-lived way station in a larger landscape of possibilities, it has already demonstrated its capacity to serve as the foundation for the most remarkable phenomenon we know, the emergence of complexity, consciousness, and understanding from the simple interactions of quantum fields in curved space-time. As we reach the end of our journey through the landscape of vacuum stability, intellectual honesty demands that we clearly distinguish between what we know with confidence, what we infer through mathematical extrapolation, and what remains genuinely unknown despite decades of theoretical and experimental progress. The story of vacuum decay is not one of settled science delivering definitive answers, but rather of sophisticated physics, approaching fundamental questions with the tools currently available while acknowledging the boundaries beyond which our knowledge becomes uncertain or incomplete. This honest assessment of our current understanding provides a more solid foundation for contemplating cosmic stability than any false certainty could offer. What we know with remarkable precision forms the bedrock of all discussions about vacuum stability. We know the mass of the Higgs boson to better than 1% accuracy, a measurement extracted from the analysis of billions of particle collisions at the Large Hadron Collider. We know the mass of the top quark, with similar precision, determined through multiple independent experimental techniques that provide cross-checks on systematic uncertainties. We know the strength of the electromagnetic force, the strong nuclear force, and the weak nuclear force at the energy scales we can probe directly with our current experimental apparatus. These measurements represent genuine achievements of experimental physics, numbers that anchor our theoretical understanding in observational reality. We also know, with mathematical certainty, how these measured parameters evolve as we extrapolate to higher energy scales using the renormalization group equations of quantum field theory. These equations are not approximations or theoretical guesses. They are exact consequences of the requirement that physics be consistent across different scales of observation, derived from the fundamental principles of quantum mechanics and special relativity. When we calculate how the Higgs self-coupling changes as we move from laboratory energies to cosmic energies, we are applying mathematical machinery that has been tested and verified in countless other contexts. But here is where knowledge transitions into inference, where solid measurement gives way to sophisticated extrapolation. The renormalization group equations tell us precisely how coupling constants should evolve, but they require input parameters that we can measure only at relatively low energies. When we use these equations to predict the behavior of the Higgs potential at energies that are trillions of times higher than anything we can produce directly, we are making an extrapolation that spans more than 10 orders of magnitude in energy scale. This extrapolation is mathematically rigorous and theoretically well motivated, but it assumes that no new physics appears between the energy scales we can probe and the energy scales relevant to vacuum stability. This assumption, while reasonable given our current understanding, represents one of the largest sources of uncertainty in vacuum stability calculations. The standard model of particle physics, which forms the foundation for all our extrapolations, is almost certainly not the final word on fundamental physics. We know it cannot be complete because it fails to account for dark matter, provides no mechanism for the cosmic inflation that shaped the early universe, and cannot be reconciled with general relativity in the regime where quantum gravitational effects become important. New particles, new forces, or new symmetries that become manifest only at very high energies could dramatically alter the evolution of the Higgs potential in ways that our current calculations cannot anticipate. The energy scales relevant to vacuum instability, typically around 10 to the 11th billion electron volts according to current estimates, lie uncomfortably close to the Planck scale where quantum gravity is expected to become important. At these energies, the very notion of quantum fields evolving in a fixed space-time background begins to break down, and effects that are completely negligible at lower energies could become dominant. We do not yet possess a complete theory of quantum gravity, which means we cannot reliably predict how gravitational effects might modify vacuum decay calculations at the highest energy scales where such effects would be most important. Even within the framework of the standard model, there are subtle theoretical uncertainties that can significantly affect vacuum stability conclusions. The calculations involve higher-order quantum corrections that become increasingly difficult to compute as you include more and more Feynman diagrams in your analysis. While the leading contributions are well understood, subleading effects that might normally be considered negligible can accumulate in ways that shift the predicted instability scale by substantial amounts. Moreover, the extrapolation to high energies probes, regimes of quantum field theory, where non-perturbative effects, phenomena that cannot be captured by the standard techniques of particle physics, might become important. Perhaps most fundamentally, our entire approach to vacuum stability assumes that the concept of a unique vacuum state remains meaningful at arbitrarily high energies. But if space and time themselves emerge from deeper structures, as suggested by some approaches to quantum gravity, then questions about vacuum transitions might be asking about features of reality that exist only as approximations valid in certain energy regimes. The very framework within which we formulate questions about cosmic stability might be limited in ways that we do not yet understand. What emerges from this honest assessment is not despair about the limits of scientific knowledge, but appreciation for the scientific process itself. The appropriate response to uncertainty is not to abandon rigorous analysis or retreat into agnosticism, but to pursue better measurements, develop more sophisticated theories, and design experiments that can probe deeper into the fundamental structure of reality. The uncertainties in vacuum stability calculations identify specific areas where progress is needed and achievable. More precise measurements of particle masses, better theoretical understanding of quantum field theory at high energies, and continued development of theories that might unify quantum mechanics with general relativity. Science advances not by eliminating all uncertainty, but by transforming vague ignorance into precise knowledge of what we don't yet know. The current state of vacuum stability research represents exactly this kind of progress. We have moved from an era where such questions could barely be formulated to one where they can be addressed through calculation and measurement. We may not yet have definitive answers, but we have identified the measurements that need to be made and the theoretical developments that need to occur. This represents genuine scientific achievement, not failure, and it provides a foundation for continued progress toward understanding one of the deepest questions in all of physics. We return now to where we began, to the quiet darkness that stretches between the stars, but you no longer see emptiness when you look into that cosmic night. The space that once seemed like mere absence, like the stage upon which the drama of galaxies and planets unfolds, has revealed itself to be one of the most sophisticated structures in all of physics. Every cubic centimetre of the universe, including the space between your atoms and the space between galaxies, thrums with the invisible presence of quantum fields that define the very possibility of existence as we know it. The Higgs field, that remarkable medium we have spent so much time exploring, fills every corner of space with its steady, unwavering background value. It is the closest thing our universe has to a cosmic constant in the truest sense, a feature of reality so fundamental and pervasive that it shapes the masses of particles, the strength of forces, and the basic rules that govern how matter and energy can behave. Like a kind of background music that plays throughout the universe, always present, rarely noticed, but essential to the harmony of everything that follows, the Higgs field provides the foundation upon which all the complexity and beauty of the cosmos rests. This field, which may be temporary on the ultimate scales of cosmic time, has nonetheless proven itself capable of extraordinary creativity. It has maintained its current configuration through nearly 14 billion years of cosmic evolution, remaining stable and reliable while the universe expanded from a hot, dense plasma to the vast, star-filled expanse we observe today. Under its influence, the first hydrogen atoms formed when the universe was cool enough to allow electrons to bind with protons. Nuclear fusion in the cores of early stars created heavier elements, forging the carbon, oxygen, iron, and other materials that would eventually compose planets and living beings. Chemistry emerged as atoms learned to share and exchange electrons in the intricate dances we call molecular bonds. The remarkable constancy of the Higgs field has enabled something even more extraordinary than the formation of stars and planets. It has permitted the emergence of pattern and information, the development of structures complex enough to store, process, and transmit the arrangements of matter and energy that we recognize as knowledge, memory, and thought. You are yourself a temporary arrangement of atoms whose masses are determined by their interactions with the Higgs field, a pattern of matter sophisticated enough to contemplate the very field that makes your existence possible. This self-awareness represents one of the most remarkable achievements in the known universe. The quantum fields that fill space have organized themselves through billions of years of cosmic evolution and biological development into configurations capable of understanding their own nature. The universe has become conscious of itself, able to probe its own foundations, measure its own parameters, and contemplate its own ultimate fate. The same physics that enables stars to shine and planets to form has also enabled the emergence of minds capable of discovering the laws that govern stellar, nucleosynthesis, and planetary formation. When you think about vacuum decay, about the possibility that our current field configuration might someday give way to a deeper, more stable state, you are participating in one of the most profound acts possible within the structure of physical law. You are using matter organized by the Higgs field to contemplate the stability of the Higgs field itself. You are employing patterns of neural activity that depend on the precise masses of electrons and the exact strengths of chemical bonds to analyze whether those masses and bond strengths represent permanent features of reality or temporary arrangements that might someday change. Whether our vacuum is absolutely stable or merely metastable on cosmic timescales, it has already achieved something unprecedented. It has provided a foundation reliable enough, stable enough, and hospitable enough to support the development of complexity, consciousness, and understanding. The atoms in your body, forged in stellar cores and assembled through billions of years of chemical and biological evolution, bear witness to the extraordinary creativity that can emerge from the current configuration of quantum fields. The thoughts you think, the memories you form, the capacity you have to appreciate beauty, to feel love, to experience wonder at the nature of existence itself, all testify to the remarkable generosity of our present vacuum state. From this perspective, the question of ultimate stability takes on a different character. Even if our vacuum is destined to decay over timescales that dwarf the age of galaxies, even if the field configuration that defines our physics represents only a temporary arrangement in a larger landscape of possibilities, it has already accomplished something extraordinary. It has created conditions where the universe can know itself, where the quantum mechanical processes that govern reality can be discovered, understood, and appreciated by structures made from the very particles whose behavior they describe. The stillness beneath everything, the quantum fields that fill the apparent emptiness of space, forms a kind of cosmic meditation in itself. Always present, always active, never resting, yet somehow conveying a sense of deep tranquility and permanence. The Higgs field that surrounds you as you listen to these words, that fills the space between stars, that permeates the vast cosmic voids between galactic clusters, maintains its background value with a reliability that has endured longer than the lifetime of any star, longer than the orbital period of any planet, longer than any timescale accessible to direct human experience. In the end, whatever the ultimate fate of our vacuum may prove to be, we find ourselves in a remarkable situation. We exist as brief patterns of complexity in a universe that has organized itself in such a way as to make pattern and complexity possible. We are temporary arrangements of matter that have become capable of understanding the principles that govern the behavior of matter itself. We are, for this moment in cosmic time, the universe's way of studying itself, of appreciating its own beauty, of marveling at its own intricate structure. Tonight, as you drift towards sleep surrounded by the invisible fields that make your existence possible, you can rest in the knowledge that you are part of something magnificent, something that has already achieved a kind of immortality through the simple act of creating conditions where thought, memory, love, and understanding can flourish. that perhaps represents the deepest form of stability any universe could hope to achieve.